Okay, just a quick summary of the different addressing modes in 8051. So you've seen register addressing, you've seen immediate, and remember immediates refer to constants, right? They're part of the instruction stream. And direct addressing, that means it's a address that is right after the opcode. And so that's a hard-coded address. And then register indirect, which we saw a little bit. There's indexed addressing mode. That's usually referring to something in the external, whether it's code or data memory. There's some implicit addressing. So we've seen A is one. Sometimes B is implicitly addressed. And sometimes the carry flag C is implicitly addressed, right? As opposed to the explicit addressed version. So ACC will be the explicit version, or CY will be the explicit version. Bit addressing, right? That's a lot like a direct address, except it refers to the bit address space. Okay, now let's look at special function registers again. So SFRs, they're located in the iData space from 80 and up to FF, hexadecimal. Now, so we'll look at these different ones over time. And these are just the basic ones. As you can see, I mean, there's space for 128, right, from 80 to FF. There are up to 128 possible special function registers, at least in this way of designing the address spaces. And in the TI CC2540, which we'll be using with the Bluetooth one, that one actually uses up a lot of the special function registers. Okay, so there are many possible addresses in the special function register space that are not defined by the original Intel, but later other manufacturers, as they add more things, they add a radio, they add an encryption chip, they add anything you want, right, on chip, then they assign address to that unit, or possibly more addresses to control each unit. And eventually they fill up all this space, right? They use up all the addresses. Then what happens? You run out of addresses. Then they'll start to use external addresses for referring to these special function registers. So that's actually what the TI chip does, and we'll go over that later. But this is the original definition for 8051. So they've defined the ports, general purpose I/O ports, which will be the topic of this week after I go over this. P0, P1, P2, P3, these are the general purpose I/O pins. There's the PSW, which we've seen. A, really, that's the ACC, right, accumulator. B, another accumulator-like register. So those have the addresses D0, E0, F0. So anything that ends with a 0 or an 8 in the special function register space is also bit addressable, as you probably recall last time. Now, stack pointer SP, that is 81 hex, okay? And that, because it doesn't end with a 0 or 8, that means it's not bit addressable. Now, DPL, DPH, those are the data pointer low or high bytes that have 82 and 83. There are a few others for timing control or timer interrupt control serial port. And now the original 8051 doesn't really do power control. What's power control? That's like going to sleep mode. And there's sometimes there may be different sleep modes. Okay, and how do you do that? Well, again, you move some bytes or some bit pattern into one of these special function registers, and then that causes not data storage, but actually some effect, right? So you could put the processor to sleep, you can set time to wake it up, or something like that. Okay, so everything that has to do with all these so-called side effects are done through special function registers. And implicit versus explicit direct addressing. So, right, just I mean this we've seen already. Implicit addressing is shorter, like E8, that actually encodes move A of R0. So that instruction is in 1 byte, whereas if it's explicit addressing, then it's like so both are like move, right? One is to move from R0 to A. The other one moves from R0 to ACC, right? That's explicit addressing. So both will accomplish the same effect, except the second one is a little larger, or larger by 1 byte. Now, so I bring this up because there are other ways of doing implicit versus explicit addressing. So, as you may know, the DPTR register, which is used for addressing external memory, whether it's code memory or data memory, you have to put the address into DPTR, and then you do the move X or move C. Okay. Now, DPTR itself is 16 bits, and there is not a single address that refers to this 16-bit pointer. But parts of it can be addressed explicitly. So you can break it into DPL and DPH. DPL is the lower byte of DPTR. DPH is the higher byte of DPTR. And I think they occupy 82 and 83 hex of SFR addresses. But DPTR itself does not have an SFR address. And this actually is pretty common. And it's not even limited to 8051. Even if you go to addMail, go to many other architectures, they also have ways of basically working with these larger pointers. Could be 16-bit, could be 32-bit, but the larger register itself does not have an address. Instead, you have to load the individual bytes of that larger pointer or larger register. Okay, and so now 8051 does have a way to load entire 16 bits of address using the move DPTR and then # some address. Okay, so you can load the 16-bit address or 2 bytes of address in one instruction. Now, move DPTR, even though the assembly looks like move DPTR as an operand, in the assembly encoding, there is no explicit address for DPTR because that's implicit as part of your opcode. But 2550 you can see in the instruction stream. And the way it's represented is actually big endian. So you'll see hex 25 following the opcode and then the 50. Even though Intel is what's called a little endian byte order instruction set. So that's kind of funny in that Intel always always takes the least significant byte first, followed by the more significant byte. But this is one exception. In the instruction stream, when you have move, that's 1 byte. And then the 2 byte address here, the 2550, they put the most significant first and then followed by least significant. Just, I mean, you may not ever have to know that, but just for your information. So that's one of those inconsistencies. But anyway, so you can achieve the same effect as using 2 separate move instructions. So you can do move DPL, the 50 hex, and then move DPH, the 25 hex, right? In this case, the DPL and DPH are explicitly addressed, okay? But the difference now is 3 bytes difference because the top one occupies 3 bytes. The bottom 2 instructions, 3 bytes each. So you take twice as many bytes to encode the effects, and actually it takes longer if you do the 2 separate moves. Okay, so So that I think there are good reasons for doing the top way, but it depends because there are times when you have to do it the bottom way separately. Maybe if you don't need to modify both the higher and lower bytes. Okay, so so here is really just to show you, like if you do move dptr of 2550, that looks like 3 bytes, 90, 25, 50, and then if you do the separate moves, each instruction actually takes 3 bytes, just because DPL has to be named explicitly, DPH named explicitly, and then you have 2 moves, right? And then so you incur twice as many bytes to encode. Now, so there are limited combinations of these addressing modes. So you may have seen this a few times already, but just wanted to show you some combinations, right? So like the move, you can have A as the destination, and then it can move from register, actually also at a register, that would be indirect, immediate, indirect, or A, immediate, direct, right, for the register as a destination, or direct address as a direct destination. Then you actually have even more options. It could be from A, immediate, direct, or another register. Okay, and so the instruction length will vary depending on which combination you choose. And so this is unlike RISC architectures you may have seen, like the MIPS or ARM or other ones where everything is fixed 32 bits. Here, it actually varies. Okay. And that's actually true with a lot of these Intel architectures. They are all variable length instructions. And for push, so yeah, this is really just to show you again. You've seen this push a direct address or pop a direct address, and now the stack pointer is implicitly addressed. Okay, and you can't say push of a register, and you can say so instead of push R0, you have to say push 0. Instead of push pop A or push A, you have to say pop ACC, and then ACC gets substituted as the E0 hex. And well, you could say push B because B actually stands for the F0 hex.